Hello everyone, my name is Maria, and today I'm going to talk about generating high-resolution Sonar data with Markov Conditional generative adversarial networks. First of all, let's look at the structure of our presentation. We will start with problem and background, and then we'll switch to why existing methods are not suitable for our purposes, and we'll finish with methodology and results, both visual and quantitative. So why use sonars at all? Well, there is a poor visibility underwater, an effect called marine snow, organic matter and dust falling underwater. That obstructs visibility a lot, so people usually use sonars. These are these bullet-shaped vehicles that fly underwater, gathering the reflected sound signal of the seabed and arranging it along the time axis of the mission. What do these actually look like when collected? So on the left-hand side, you can see aerial view of a few short missions. On the right-hand side, you can see what teleoperators see once the vehicle gets extracted from under the water and the data gets inspected for objects of interest. So why generate these? Well, it's pretty self-explanatory that the sonar data are expensive and time-consuming to gather. These involves loads of quite complicated hardware and hence is expensive and rare, which triggers commercial sensitivity and privacy issues. Often companies are not capable of sharing this amongst themselves. So there is numerous potential uses for synthetic data. We are only going to cover two today. One of them is visual simulator for training teleoperators, and the other one is data augmentation for autonomous target recognition and detection systems. That's for the case when you don't have access to enough real data, and synthetic is the best you can get. There are actually models that are famous for their realistic data generation. They're called generative adversarial networks. And here you can see a few examples of image translation, which is a controlled image generation facilitated by conditioning on either semantic maps or something else. For instance, these examples feature semantic maps to street view, aerial view to real maps, and sketches to images, and so on and so forth. So the vanilla GAN architecture usually features at least two networks. One of them, generator, inputs the noise vector and outputs something hopefully realistically looking. Then the other one, discriminator, takes in this generated output along with the real data and tries to label both as either real or fake. Target of the generator is to fool the discriminator. Target of the discriminator is not to be fooled. These usually train simultaneously from scratch, and under normal conditions both improve via competition. Now, why the existing ones are not suitable for our purposes? Back in 2014, when GANs were just introduced, they usually would generate images of size 128 by 128. Nowadays, situation improved a lot, and we can get high-resolution imagery of size 1000 by 2000, or maybe even a little bit further than that. Now, the sonar data are more like 1000 by 300,000 pixels, and that's for short 2-hour mission. Longer missions can run 14 hours and over. And we need all of this data in one piece because that's how the real data look like, continuous and smooth. So piecewise generation is not necessarily an option. So we came up with this idea that we could apply Markov assumption to our generative adversarial networks. What we do, we use the existing method called pix-to-pix, which translates semantic map into something hopefully realistically looking, but we also condition it on a small snippet of a previously generated image. That way we have both. Piecewise generation that looks smooth and continuous like real data do. Now, not everything can be incorporated into semantic maps. For instance, turns. So the way we implement turns in our algorithm is we overlay grayscale semantic maps with yaw and pass it as a condition for the generator. Now, in summary, our MC pix-to-pix training looks like following. The semantic maps, the yaw data, and the condition, which is this 20 rows of previous image, are passed to generator. It generates something hopefully realistically looking, and then this data, along with the conditions and semantic maps and real data, gets passed to discriminator, which then tries to distinguish real from fakes. Now, once trained, we do not really need discriminator, so we discard it completely, and we use just generator for the testing stage. In testing stage, the process is run recursively. So generator receives semantic maps, your data and condition, which is 20 rows of the previously generated image, produces something hopefully realistically looking. We take this output, we chop off last 20 rows, and we pass it as a condition for the next cycle of generation. This process runs recursively for as long as you need, depending on what length of the mission you'd prefer. Now, what's great about it is that it is also useful for access to low computational resources. You can even run this generator on normal gaming GPU. You don't need anything more sophisticated than that. Now, does it work? Can you tell real from fake? One of these sides is real and one is fake. Which one's which? So here we go. The right-hand side was generated with our MC Pix2Pix method, and the left-hand side was real. It's not only you, real human experts are also unable to tell them apart. But a little bit more about it further along. And now we're going to focus on it a little bit further, so you can see the semantic maps on the left. Here the color encodes the types of terrain, such as flat, ripples, rock, and so on and so forth. The next two are our baseline methods, Pix2Pix and Pix2Pix with sigmoid blending. So Pix2Pix is the underlying method we base our MC Pix2Pix on. You can see how it translates image piece by piece, and you can clearly see the two tiles there. Sigmoid blending is just some post-processing, so if you'd like to generate your imagery with Pix2Pix and then try to blend it together, that's what it would look like. And finally, there is our MC Pix2Pix and real data. Now, everything on its own looks relatively realistic. However, you can clearly see the smoothness at the transition border, and you can clearly see we win this round. And here is just another image to show the same point. So, how does it summarize in numbers? We asked 30 real human experts to label the data. These are people who work with these images for ages, and what they were asked to do was just to label the image that appears on their screen, and we show them images generated by Pix2Pix, sigmoid blended Pix2Pix, MC Pix2Pix, and real data. So you can see that for our method, the accuracy of labeling the images correctly is 52%, which for two-class problem is actually near random chance, so real experts cannot tell them apart. Then the next important piece of information is synthetic data labeled as real, and ours look pretty bad at 54%. However, once you know that real data labeled as real are actually scoring 66%, it's a pretty good result. Now, although our method is instantaneously useful as visual simulator for training human operators, there are other means of applying it. For instance, you could use it to boost the training of your autonomous target recognition or detection systems. Here we just take the increment of adding our data into the training set. So you can see training on real image only, plus noise or plus Sonar sim, which is a mildly realistic hard-coded simulator, and then plus our MC Pix2Pix. And the increment suggests that it's clearly very beneficial to use our synthetic data for ATR training. Now, that's about me done. It was a pleasure presenting for you guys. Please do let me know if you have any questions, and thanks for watching!